SwayamPrabha. Digital India. Educated India.
Welcome. So we are now in lecture 9. So in this lecture we will learn what is strong form and what is weak form. So to start with, we'll use what we have learned in the previous lecture. For instance, the Euler-Lagrange equation and its boundary condition. Then we will go for bar and beam problem. So we will briefly discuss that. Then we will introduce the weak form or basically the weighted integral statement of a differential equation. And then we will also learn that how bilinear and linear forms are defined, what we have learned. So for instance, we have learned the weak form Euler-Lagrange equation of a functional. So if I have a functional I, so this functional can be of this form, that is x1 to x2 f of x y y prime y double prime dx. Then this strong form functional we can minimize or extremize, that is first variation of the strong form, first variation of the functional is 0. So that is the extremization condition. Now this leads to Euler-Lagrange equation. For instance, in structural mechanics application, let us see some problem. So a simple bar with a load, distributed load, and there is also a point force P applied. So this distributed load is, say, Q and a point force applied. Now the length of the bar is L, length of the bar is L, area A, Young's modulus E. So let us take constant for the time being. So what are the boundary condition of this problem? We all know what are the boundary conditions. So if along x-axis the degrees of freedom is u, it is a 1 degree of freedom problem. So it's a one-dimensional problem. So at x equals to 0, the displacement u is 0, right? And at this point we also know that the condition, that is sigma dot n, should be equals to the traction force at this point, that is the at x equals to L. So this is at x equals to 0. So at x equals to L, we will have AE du dx is the stress, right? And then dot product with n is one dimensional, so 1, so that is equals to P. So this is the boundary condition at x equals to L. Now we what we did is that we found out its energy densities, or the potential energy we know. So that is equals to 0 to L A by 2 du dx whole square dx, then minus this condition because you have a UDL, so that is the work done. So 0 to L QU dx, and you have a load at x equals to L. So that is P into U at L. So that is your boundary condition. Now by this is your energy functional or the potential energy functional. Now by minimizing this potential energy function, we get the Euler-Lagrange equation or the differential equation. So what is that differential equation? Differential equation is our AE. So here I am taking E and A are constant. It can be function of x also. So then this A term will be, one of them will be inside. So dx square equals to q0 or q. So this is the basic differential equation. Now this differential equation is valid from x equals to L to x equals to 0. Now this is the Euler-Lagrange equation. Now associated boundary conditions also we know, that is u equals to 0 and at x equals to 0 and AE du dx equals to P. So at x equals to L. So now similarly for the, if I do for the beam problem also we have seen beam problem. So here let us take a simple beam, simply supported beam. So here I think we have done this in the previous class. So here it is Q. So now let us take EI constant, EI, and area is also constant, and then the boundary condition we also know, if this is the displacement, that is this is x axis and this is y axis, this is also a one dimensional problem. So W is the displacement. So here vertical displacement or the transverse displacement is W. Now here W is equals to 0 and moment here is 0. So that is EI d2W dx2 equals to 0. So here at x equals to L, W is also 0 and moment, that is EI d2W dx2 is also 0. So similar to previous problem, the bar problem, we have found out its potential energy. So the potential energy is 0 to L EI by 2 d2W dx2 whole square dx minus your integral 0 to L QW dx. So now similar to that variational statement or the minimization, extremization, if we do, then we get the differential equation of that beam. So that is EI d to the power 4 W dx to the power 4 equals to Q0, and then the boundary condition W0 equals to WL equals to 0 and EI d2W dx2 equals to at x equals to 0 and EI d2W dx2 at x equals to L equals to 0. So now if you look carefully, so what we have done here is that this is the differential equation of the problem. This is the potential energy of the problem, and this is the differential equation, or so this is ODE because this is one dimensional variable. So differential equation of the problem, and similarly for this is the potential energy and this is the differential equation. Now this we derived from here to here. So here to here we arrived by minimizing the potential energy, or first variation we made it 0. So this is our what we have learned. So this differential equation, or the Euler-Lagrange equation specifically, is known as the strong form of the problem. What do we mean by strong form? That means these conditions has to be satisfied each and every point of the body, right? So that means at each point of the beam, naturally a continuous structure will have a finite, you will have an infinite number of degrees of freedom. So this differential equation is valid at each point on the beam. So that's why it is strongly applicable, or when you find a solution of the problem through this differential equation, then strongly you have to satisfy the fourth order derivative of the W multiplied by EI equals to Q0, this condition, and it's obviously the boundary condition. A differential equation is incomplete without boundary condition. So boundary condition is very important. So that's why we call this as strong form. So for instance, so this is nothing but the strong form of the problem. So this is nothing but strong form. Of the problem. Now suppose we don't know its potential energy and we only know the differential equation of the problem. Then how should I solve? So naturally here we start slowly entering into the finite element. Naturally we need to approximate this solution. For instance, in case of a beam and bar problem, the approximation, getting an approximation is not very difficult, because this problem can be solved exactly. But our objective is here to how to approximate for a general problem, and we will demonstrate it with the known solution of the problem. So that's why we have taken this kind of problem. Now to approximate this W, we can choose, or we can approximate W. Suppose for the beam we can choose any polynomial and any say C0 plus C1 plus C2, so like this, and this can be applicable for any problem. So like this we can approximate this problem, but this approximation will not lead to, this approximation need not lead to a unique solution of the problem, right? Because it needs to satisfy boundary condition, even though we can find out the some constants from the boundary condition. But if we substitute this here, these coefficients or the unknown values of these coefficients C0, C1, C2, C3, we may not able to find out uniquely, because that condition, because this will lead to a single equation, for instance, and if you have 3 or 4 constants, then you may not able to find out at all, because what you will do in that case, you will equate the polynomial order in both sides, and you may not lead to a unique solution of the problem. So the takeaway from this is that we have to devise a method by which we can get an unique solution, first of all. Second, we have to find out, in a sense, that the solution can be easily found out. For instance, in case of a finite element, we do it over the element wise and over the subdomain wise. So for instance, if there is a general structure, we divide it through the elements. So these concepts we'll go into detail, and then we'll find out how to do those things. So now, so the basic problem with this type of approximation is that you may not able to find out unique solution through any general approximation function. I am not telling that you cannot find out, you can, for certain approximation you can find out, but our objective is how to ensure that these our approximation or our formulation in such a way that it always leads to a linear independent equation, and that thus leads to a unique solution. So basically, if you substitute this kind of approximation, then you may not get the linearly independent equation. So that's why the weighted integral technique, or the weighted integral statement, or sometimes known as the weak form, is proposed. So first let me tell what is weak form. So weak form, suppose you have a differential equation. We can choose this differential equation. So that is a simple differential equation, and then we'll explain it to explain for beam also. So suppose that differential equation AE d2u dx2 equals to q0, and then the boundary condition is u equals to 0. So this is at x equals to L to 0, and this is x equals to 0, and this is AE du dx is P at x equals to L. Now we can here we assume that we know the differential equation and we want to solve this problem. So naturally, practical problems, or where the realistic or real life problems cannot have the exact solution. So that's why technique like finite element method is required, because we need to always find out the approximate solution or the numerical solution. So this numerical solution, finding out numerical solution is nothing but the approximation of the original problem. So now the weak form is essentially the weighted integral statement of the strong form. So let me write it. So weighted integral statement of the strong form. So now how can I find out this weighted integrals technique? So naturally, the word weighted means there is a weight function involved, right? And this is an integral statement. So let us suppose I choose a weight function. Here let us choose a v is a weight function. So this weight function, I will come to this, what is the property of this weight function required in due course, but let us see this how this we can write the weighted integral statement. So naturally, the weighted integral statement of the strong form means this 0 to L, the integral, then the AE, W is my weight function, then AE d2 u dx2 plus q0 equals to 0. Not 0, the weighted integral statement. So so this is my weighted integral statement. Now that means that sorry, this weight function is W, not W, this is V. So this weighted integral statement is the differential equation itself. So if you look carefully, this is nothing but the error of the differential equation, and this weighted integral statement, I say that weighted integral statement will be 0. So that means with respect to some weight function, this quantity must go to 0. So this is the basics of the weak form. Now weak form, another property is that weak form, that it reduces the differentiability requirement of the strong form. So that means if you look carefully, that when we approximate the u here, u will be at least twice differentiable. So when we approximate u, so at least 2 times differentiability is required in the this approximation to solve this differential equation. Now we will see that how we can find out, or how we can reduce the differentiability requirement. So that leads to integration by parts, which will transfer the differentiation to the weight function itself. So naturally, if I do that, then I will get some boundary condition term. So because there will be some boundary term will be there. So naturally AE du dx into W or V here. So this is nothing, the weight function is V at x equals to 0 and x equals to L. So now this again the by parts. So this will lead to dv dx, and this is AE and du dx. So this is my integration by parts, and this term let me keep it same. So 0 to L Q0 V dx. So now if you look carefully, this when we do this by parts or integration by parts, when we do, then we can see that this condition that is already appeared as in terms of boundary conditions. Now these boundary conditions we have also see that when we minimize this potential energy, then this boundary condition automatically arises. So naturally in the weak form, this natural boundary condition, so this is a natural boundary condition, so natural boundary condition automatically arises. So here one more thing, that the function here, it also specifies what should the weight function must satisfy. So if you look this weight function as per our previous knowledge, that this V must go to 0 at the boundary. So that leads to admissibility condition or the admissible approximation. So admissible or the admissibility criteria. So now, so this V must be 0 at x equals to 0 and x equal to L. So this condition, if you have remembered the Brachistochrone problem where we have discussed this, so this is a cycloid of the Brachistochrone problem. So our variation for this problem, we constructed that this could be this could be this. So these functions are approximation or y tilde. So these are nothing but exact solution y plus delta y. So if you look carefully that this delta y at these two boundary points must be 0, because the variation otherwise will not be admissible. So similar condition is applicable here. So V has to satisfy, or the homogeneous, or the V, the weight function has to satisfy the homogeneous boundary condition. So which leads to one of the important criteria for choosing the weight function, that it should satisfy homogeneous boundary condition of the field variable, or homogeneous boundary condition. So what is homogeneous? That means V should be 0 at the boundary. So naturally in some problem, for instance this problem we are discussing here, in this case there is a load here P, and there is also a UDL load along x. So this condition needs to be satisfied here. So this at x equals to 0, naturally that V should be 0, right? Otherwise even though if I specify a displacement here, for instance problem of this type where we learn that probably we have seen earlier that there is a some spring is there, and there is a force here. So this type of problem where the spring stiffness is K, right? Here displacement at this point is not 0. So displacement is, say, u equals to u0. Obviously u0 will govern by the spring. So I will not go to the detail how to do that. So this will so that means that my central idea is here that u0 need not be your 0 boundary condition. Even though u0 is the boundary condition that is coming here, then non-zero boundary condition, then also the admissibility criteria leads to homogeneous boundary condition of V. That means V should be 0. So now if you look carefully, so what we have learned, so weak form is the weighted integral statement of the strong form. Naturally we can reduce the differentiability requirement of the approximation of field variable, which is u here, by transferring the derivative to the weight function. So if you look this carefully, this is nothing but the this transfer of the differentiability happened in the V variable. So V is nothing but the weight function. So that means to solve the problem in a strong form, you need a higher order differentiability requirement, but in weak form or the integral statement of the problem, if we do by parts, we can reduce the integrability or differentiability of the problem. Now so let us see. So here if you look carefully, that this is actually will lead to my finite element stiffness matrix. We will come to that later. Now this condition on the other hand, if you look here, that here this V is can be anything. So V is not necessarily 0 here, because here there is no Dirichlet boundary condition specified. Here the force boundary condition is specified. So naturally this V need not to satisfy this homogeneous boundary condition. So that means this quantity is specified here. So naturally this will give me the required boundary condition. So by doing integration parts of the differential equation or the forming the integral statement. So there are 3 steps. So first you form the integral statement, then you take the integration by parts. So the condition for integration and the condition for choosing the weight function is that V has to satisfy the homogeneous boundary condition when U is specified. So that is second condition, and natural or the consequence of this integration by parts is that we naturally arrive the natural boundary condition or the Neumann boundary condition. So but if you look carefully, that we have not satisfied the U equals to 0 condition. That means when you discretize or when you solve this problem finally, then additionally you have to impose the Dirichlet boundary condition. So in the weak form, natural boundary condition, natural or Neumann boundary condition appears automatically. So this is one advantage. So if you don't solve in the integral way or integral sense, then you have to satisfy this natural boundary condition specifically. So in weak form, this is a major advantage. By taking the integration by parts, we can reduce the differential requirement and automatically natural boundary condition pops up. So this is the one of the biggest advantage in the weak form. Now sometimes it is also known as the variational statement of the differential equation. Now if you look carefully, this is very similar to what we have done in the previous energy minimization or the potential energy extremization problem, where the variation is very much correlated with the weight function here. Now before we proceed, so in case of a beam problem, we can just extend it for the same way we can extend it. Now let us define some of the quantities which we need later. So that is bilinear form and linear form, or bilinear function or functional or linear functional. So for instance, the bilinear form, linear form means we know a function which is a linear function. How do we test a linear function? Simple fx equals to suppose x square. So this function is not a linear function. Why it is not a linear function? So how to test that? So f of, suppose I just do x plus y, okay, another variable I do. So naturally x plus y whole square, so which is x square plus 2xy plus y square. So this is f of x plus f of y plus 2xy. So naturally this is not a linear function. So what is the condition for linear function? So if I just do a definition, so f of ax plus by equals to a of fx plus b of fy. If this is satisfies, then we call this fx is a linear function, where a and b are in real line or the scalars. Okay. Now in case of a linear form, similar definition we can find out. So suppose there is a linear form L is a function of v, then this linear form is a this functional or the form is a linear form if it satisfies, that is L of a v plus b of w equals to a of L of v plus b of L of w. So where again a and b are scalars. So this is called a linear form. So this is known as the linear form. Linear form. Now what is bilinear form? So bilinear form again, suppose B of V comma U is my bilinear form. So let us now define first what is bilinear form. So in case of a previous problem, so let us now define what is the bilinear form here. So so the weak statement of the bar problem, that is weak statement of the bar problem or the variational statement of the bar problem is nothing but that is A du dx v at x equals to 0, x equals to L, and then naturally x equals to 0, v has to be 0, so this is cancelled. So I can write it in terms of only at x equals to L. Then integral 0 to L a by 2, not a by 2, a into d v dx dv dx into du dx. So into dx, and then integral 0 to L q q0 v dx. So this term is the linear form. So let us now define the linear form, that is L of v is essentially integral 0 to, so minus, let me take the minus, 0 to L q0 v dx plus a du dx at x equals to L. So this is the linear form. So if you now apply this thing here, then it will satisfy this. So this is the linear form. Linear form. Now the other part, which is this, I define as my bilinear form. So what is this bilinear form? That is B of v comma u is integral 0 to L dv dx a du dx into dx. So this is, I am saying, bilinear form. Now what is the definition of a bilinear form? The bilinear form has to be linear in each of its arguments. So for instance, there are two arguments. In the linear form there is only one argument. So in the bilinear form there are two arguments. So naturally the linearity has to be done in terms of two arguments. So suppose I choose B of alpha 1 v1 plus alpha 2 v2 comma beta 1 u1 plus beta 2 v2 u2, then the bilinear, if the form or the functional is bilinear, then it's it will give me like this. So alpha 1 beta 1 b of v1 comma u1 plus alpha 2 beta 1 b of, this is comma, so v2 u1 plus alpha 2 alpha 1 beta 2 b of v1 comma u2 plus alpha 2 beta 2 b of v2 u2. So here alpha 1 alpha 2 beta 1 beta 2 are scalars. Okay, so now if you look carefully that this is linear in both the arguments. So that means if I just keep constant there, this is, then this is the first two term is giving me the linearity in argument of v, and then if I choose this term, then this will be in terms of this. So this is, that's why this is the condition for a bilinear form. Condition for bilinear form. Now, so here let us see whether this bilinear form we have seen. So this is naturally a, if you just substitute this, so derivatives are commutative, so naturally it will satisfy this bilinear form. So another important thing is that if a bilinear form is symmetric, that is v of b of v comma u equals to b of u comma v, so then we call this is a symmetric bilinear form. Symmetric bilinear form. So now naturally this is a symmetric bilinear form. So if I just take this quantity this side and this quantity this side, this will give me b of u comma v. So this is a symmetric bilinear form. So now let me write out the weak statement in this bilinear and linear form. So that is your, so this quantity is nothing but the b of v comma u, and this other quantity is l comma v, l of u. So this thing I can write it in short, that is b of v comma u equals to l of v. So this is my weak statement or the variational statement. Now where b of u comma v comma u is my bilinear form, that is 0 to l dv dx into ae du dx into dx. So if you look carefully that this is something related to the strain energy. Now means the derivative of the strain energy. You will see this later. Now this L of V is nothing but minus integral 0 to L Q0V dx plus your the boundary condition. So naturally this is P, I can put P into V at L. So this is my for the bar problem, this is my weak statement. Weak statement. So we learn, I stop here. So we learn mainly three things here. One is we learn what is strong form. So naturally the strong form is the coming from the energy minimization. So potential energy minimization. So if this is a potential energy, we get the Euler-Lagrange equation, which is nothing but the strong form. So including boundary condition. Now if I have this strong form, then if I just do its weak form, so or weighted integral statement. If I write its weighted integral statement, so here what we did is this. Okay, the first variation of the this thing is 0. So now if I make the weighted integral statement or the weighted integral statement of the Euler-Lagrange equation, and if that I make it to 0, then we get the weak form of the differential equation. Again, from the weak form, if it is a symmetric weak form, then we can go back to this very easily. So if this weak form contains the symmetric bilinear form, then we can go to the potential energy by some manipulation. So I will cover this in the next class. So here we stop, and so in this class we learn weak form, strong form, and the different parts or different things in the weak form, that is bilinear form and the linear form. So thank you.